Section 11.3, and what we're going to do is we're going to take our inductors and we're going to take our resistors and we're going to put them in parallel. And we're going to ask, what is happening now? And so that'll just be one of those wonderful things. So if I have some power supply, it has to be an AC power supply, otherwise the inductor is just a hunk of wire. And so I got some current going through the inductor. That's not an inductor, but that's okay. Current going through the inductor.
Is that 2 or?
This is a resistor over here, in case you're wondering. And a current going through the inductor. And they're in parallel, so they have to add.
In parallel.
Yeah, they're in parallel. So that means in series, the current has to be the same through both. I don't have a choice. In parallel, they have to add. So, but they're 90 degrees out of phase. So my current across the resistor is that way, and my current across the inductor is that way, and those are right angles. And so that means the current total is going to have to be the square root of the current across the inductor, through the inductor squared, plus the current through the resistor squared. And even though I said those things backwards, I wrote it down right. And that's because they're at right angles to each other. Now, how about the voltage? The voltage across the resistor, the voltage across the inductor, the voltage of the source, all has to be the same. I don't have a choice there. All right, so we have some pictures. Okay, now, if I look at the impedance of a parallel system, so I got this system that's in parallel again. The impedance still has to be the voltage, whatever the voltage is across, divided by the current total. That's still going to have to be the impedance. I don't have a choice. My total current is going to have a magnitude, but it also has to have an angle, right, associated with it. Arctangent of the inductive guy divided by the resistive guy. And this, because turns out my real current is that way and my inductive current is going to be this way, so my Z is going to have a negative angle associated with it. So that's why we see negative angles in places. All right. We can also say Z, the impedance, is going to have to follow the 1 over 1 over rule. So that's going to have to be the square root of 1 over x of L squared plus 1 over R squared. So that's cool. So not only are we have to follow the 1 over rule, but these guys are 90 degrees out of phase with each other, so we have to follow Pythagorean theorem and put a square root over it too. So isn't life wonderful? I think so.
You start singing Christmas songs then?
I think I will, yeah. Then we have subseptance and admittance. So on page 347, SUSCEPTANCE, and admittance, MIT, TANCE. And these are so important, I've yet to put those terms on any test in my entire life. So that's how important they are. And so if I have resistance only, then my conductance is 1 over R. And so that's fine. But if I have reactance, then my subseptance B I won't spell it again because it's really bad. So that whatever that is, B is equal to 1 over x of L. And my admittance, which I have to spell again because I can't see it. Where's the admittance? Y. Okay, so Y, my admittance, is going to be the square root of, this is BL, squared plus G squared. And again, those particular terms, admittance and subseptance, and calculations of them, I've never used on any test in my entire life, including grad school. So you have days like that. Now, there is going to be a frequency response in the parallel circuit. So if I have some parallel circuit sitting there, then it's just so bad. Much better is 2 pi FL. So if I take my frequency and I vary it up and down, then this guy's going to be changing up and down, which is going to change the currents going through these guys, which is going to change the total current, which is going to change everything else that can be changed. So that's just another cross we have to bear. Okay. Let's see if we can find a problem to run. Problem number 22, maybe? Yeah, problem number 22. That sounds like fun. 22. And calculate the impedance of the circuit. All right, so I've got this guy doing that, 120 volts. I've got this guy here. Well, I'm going to throw in an ammeter. That was good. And that guy there, I'll come over here and throw in another ammeter. Resistor there. LR. 0.8 amps. 0.12 amps. Now I wouldn't write them that way, except I don't want to copy directly out of the book. So total current is the square root of 0.8 squared plus 1.2 squared equals. Now, as luck would have it, I don't have my calculator sitting over here being charged under the lamp, so there's absolutely no way I can do that calculation for at least a half second. 0.8 squared plus 0.12 squared equals square root 810. 810 milliamps. 810 milliamps.
Concentrate.
So my impedance is going to be the voltage divided by the total current, which is going to be 120 divided by 110 milliamps. And so 1 over times 120. Looks like 150. 150? Yeah, 150 ohms. 150 ohms. I still need an angle. So my angle as a reference angle, arc tangent, the I sub L guy, 0.8 over 0.12 equals, and it'd be nice if that looked like arc tangent and didn't look like squiggle. 0.8 divided by 0.12 equals arc tangent looks like 81 degrees. 81 degrees? Yeah, 81 degrees. So we'll call it angle minus 81 degrees. Because the impedance, this guy's at an angle of 81, so that makes this 81, or is this minus 81 and that makes that positive 81? This is minus 81, that makes this positive 81. There, that's better. Which implies minus 81 degrees. Okay, well I guess I did number 22. So now we're going to look at, let's look at the next one if we need to. 27. All right, we'll do 27 next. Number 27. Calculate the components and circuit currents shown in A below. All right, so I've got this guy, I've got 3 volts. I got an inductor, got another inductor, and I got a resistor. And I got a drawing problem again, continually. Okay, 22 millihenry, 15 millihenry, 510 ohms, 5 kilohertz. L1, L2, just R. Okay, well, we'll call, what are we supposed to do? Calculate the component and circuit currents. Okay, so the current through the resistor is 3 volts divided by 510 ohms. All right, well, that was easy. 3 divided by 510. Call it 5.9. 5.9 milliamp. What, volts?
No.
3 divided by 510. Yeah, 5.9 milliamps. Okay, that looks good. All right, now, the current through L1, 3 volts divided by 2 pi, 5 kilohertz, 2.2 millihenry. Okay, so I need to divide by x of L, which I don't have, so I got to calculate it, 2 pi 5. Well, the kilo and the milli cancel each other out, so I can go 3 divided by 2 divided by pi divided by 5 divided by 2.2, and as long as I don't lose power, I'll get an answer, and it looks like 43. That can't be right. Yeah, it could be 43. 43.3 milliamps. You're right, 0.4. Somebody complaining about the 0.3? You were? All right. You were going to, but I corrected it soon enough. All right, L2, 3 volts divided by 2 pi 5K times 15 millihenry. Was that 2.2 or 22? That's 22, isn't it?
What's happening?
All right. Who's going to complain about that? Okay, so that goes there, this comes out of here,
I wrote 22.
and this is 0.3. Okay, so that's better?
That's better.
All right, now, if I multiply my answer I have in my calculator by 22, times 22, and then divide it by 15, I will have the answer to the next guy without doing much. Of course, I still can't read it, but that's beside the point. Okay, so I don't think I did that right, so I guess I'll have to do the whole calculation. 3 divided by 2 divided by pi divided by 5 divided by 15. And I end up with 6.4. 6.4 milliamps. So I have the component currents. Now I need to find total current. Current total equals square root of 5.9 milliamps squared plus 4.6 milliamps plus 6.2 milliamps, the quantity squared.
It's killing me.
All right. What's the problem? I didn't think so. Plus 0.0043 equals squared plus 5.9 W3 minus squared equals square root 12.2. I have a total current of 12.2 milliamps, and this guy is angle minus 90, and this guy is angle minus 90, and that makes this guy theta reference, which means the first quadrant answer, which I really don't care about because I want a fourth quadrant one. Absolute value of the y component 10.7 divided by 5.9. 10.7 divided by 5.9 equals arc tangent. (61°). 61 degrees, which I'm going to put back there, angle minus 61. Okay, so I did that, and I did that. The next one is 33, and 33 we can't do that. All right, so we'll proceed on to section 11-4. Okay, in 11-4, we're going to have some AC circuit. We're going to have resistor in parallel with an inductor and a resistor, or we're going to have a we could have a inductor in parallel with another inductor, in series with an inductor and a resistor, or any other combination of anything. I mean, could be whatever it is. All right, so what we're going to end up doing first is we're going to have to go and calculate the parallel circuit guy first, and then get something there, and then we're going to go and add it into this guy, and then we're going to get total current. Once we get total current, we're going to get the voltage across this guy with the voltage across that guy. That's going to tell us the voltage across the parallel guys. Then we're going to find currents across each of them. Okay, was that good enough?
That was clear.
That's exactly what we did in chapter 9, right? So we calculated the parallel guy first, the total, in this case, impedance second. We use the total impedance to calculate total current. We use the total current to calculate the voltage across X1. This we're going to call him X1 because it might be a resistor, it might be something else, we don't know what it is. With that, we're going to find the voltage across the parallel path as being the voltage source minus X with the voltage across X1. And then with that, we're going to calculate the currents through the other guys. And if they have to calculate powers, we'll do that too. All right, so that's the plan. I'm sticking with it. Is there anything else going on?
Chapter 12.
Yeah, that's about all there is. All right, so let's, now that we know what we're doing, we can go back and do problem number 33. Yeah, moving right along. Just in case, we'll open multisim, just in case. Because the instructor might get the wrong answer. I know that's hard to believe, but you know, it's possible. Now, multisim is very easy to get the magnitudes of everything. It's not that easy to figure out what the angles are of everything in multisim. So, but if you have to get halfway there, then you'd use multisim to get halfway there. So I'm looking at problem number 33. And 45A. All right, so I got this guy sitting here, and I've got a resistor, and I've got an inductor, and I got another resistor. So 4 for that drawing. 10 volts. Is that an RMS voltage? Is that a peak voltage? Is that a peak-to-peak voltage? If it doesn't say anything else, no, it doesn't. It doesn't say anything else, it's RMS. Right. But if I do the calculation with this as RMS and I get answers, right? Or if I do that as peak and all my answers are in peak, or if I do it with peak to peak and all my answers are peak to peak, guess what? All the magnitudes are going to be the same. But if I say this is peak and I want these as RMS values, then I'm hosed. Okay, that's not going to work very well. 6 kilohertz. All right, I got that. 330. Got that guy. 1.8K. The inductor, 50 millihenry. So, what do we need first? We need X of L. 2 pi 6K 50 milli. Okay, the milli and the K go away. So I got 3,600. I got 600 pi. Okay, so 600 times pi equals 1.88. 1.88 kilo ohms, angle 90 degrees. Okay. Now we need the impedance of the parallel path. 1 over the square root of 1 over 1.88K squared plus 1 over 1.8K squared equals. Okay, that looks good enough to me. Okay, 1.88 1 over squared plus 1.8 1 over. Oh, bummer.
Can you add the resistor with that?
Not yet. I'm finding the impedance of the parallel path,
Okay.
not the total impedance. That's what this little 2 lines over here mean. I could say this plus that other resistor. I'm not doing that yet. All right, so where was I? 1.88 1 over squared plus 1.8 1 over squared equals square root 1 over. So I've got 1.3K. 1.3K. Now I need a phase angle with that. So my phase angle is going to be the arctangent of the admittance, the reactance. Yeah, the reactance divided by the resistance. 1.88 divided by 1.8 equals second function tangent. 46 degrees. 46 degrees. Angle 46 degrees. Okay, so now I need the impedance total. So the impedance total is going to be 330 ohms plus 1.3K angle 46. Okay, now I can't add a real number to a polar coordinate. Okay, so I got to change my polar coordinate guy into a rectangular guy, 330 plus. So I'm going to take my calculator and I'm going to go 1.3, the XY key, 46, the equal key, second function, polar to rectangular key. Now, for those with graphing calculators, there are other ways to do this. I hope you know how that is. If you don't, you can see me after class sometime and we'll explain how to do it on your calculator. Okay, so I'm going to do that on my calculator. 1.3 XY key, 46 equals second function, change to rectangular, and the calculator says 1.059. We're going to call it 1.1. So that's 1100. XY key again, 750. We'll call it 750 plus 750 I. Okay, so that's what I'm going to do. So if I didn't do that, I would say the x component is going to be 1.3k cosine 46, and the y component is going to be 1.3k sine 46. So I could do that as well if I didn't want to use my polar to rectangular function on my calculator, which is the only reason that you're going to have a TI-36 to begin with, is to do that because it's so easy to do. What?
On the X, 1.3.
This is the XY key, which on my calculator is the one under the second function key.
No, I'm talking about the second line, right below that, which says the X equals.
Here?
X equals 1.3K cos.
Is that cosine?
Cosine, yeah.
Yeah, that's a cosine. Yeah.
Thank you.
Cosine, sine. So if I weren't going to do that, I could do this. All right, now that I've done it, my real portion adds, my imaginary portion stays the same. So now my impedance, total impedance becomes 1,430 ohms, 1,430 plus 750I ohms. Now I'd want that to be a polar coordinate guy, not a rectangular coordinate guy. So this time I'm going to do the same thing in my calculator. I'm going to go 1430 XY key 750 equals third function, change it to rectangular, and I'm going to see 1.6K angle, 1.6K ohms, angle minus 27.6. No, it can't be minus 27.6. How did I get a minus guy in there? 1430 XY key 750 equals third function, boom. Okay, that's right. 27.7 degrees. We'll call it 28 degrees. 28 degrees. So that's going to be my total impedance. With my impedance, I can now calculate total current. So total current is going to be voltage source divided by the impedance total. And anybody remember what the source was? 10 volts. So 10 volts divided by 1.6 K ohms angle 28 degrees. Okay, so my angle is going to be minus 28 degrees because it's positive in the numerator, in the numerator, so in the denominator it's going to be negative. All right, so 10 it's 1 over 6 times 10. 6.2 milliamps. 6.2 milliamps angle minus 28 degrees. So that's my total current. My voltage through resistor 1 is going to be the total current times resistor 1. 6.2 milliamps angle minus 28 degrees times 330 ohms. 330 ohms. Okay, so I've got 6.2 milliamps already in my calculator times 330 equals 2 volts. Okay, so we'll call it 2 volts. 2 volts angle minus 28 degrees. Okay. The voltage across the parallel path. Voltage across the parallel path is going to be voltage source minus voltage across resistor 1. 10 volts minus 2 angle minus 28 degrees.
Thank you, sir.
Okay. Now I can't subtract those, so I'm going to have to put the 2 angle minus 28 into rectangular form. 10 volts minus, okay, so I go 2 xy key 28 plus minus key, change to rectangular form, and I have 1.8 probably minus xy key 0.94 I volts. Okay, so I'm going to have 8.2 minus plus 1.94 I volts, and then I want to change that back into polar form, so V across the parallel path, 8.2 xy key 0.94 equals change to third function, change to polar, 8.25. Okay, we'll go with 8.25 at 6.5. Okay, so 8.25 volts, angle 6. That doesn't look like a 6. 6.5 degrees. Okay, now I know the voltage across the parallel path. I can find the current through the inductor, and I can find the current through the resistor. All right, so the current through the inductor, did we figure out, yeah, there it is, 1.88 K. All right, so 8.25 volts, angle 5.6 degrees, divided by 1.88 K, angle 90. The current through the resistor, 8.25 volts, angle 6.5 degrees, divided by, what was that resistor, 1.8K. Okay, well this is going to be angle 84, 83, 83.5. 83.5 with a minus sign. 8.25 divided by 1880 equals 4.4. So 4.4 milliamps. And then this guy here is going to be at an angle of 6.5 degrees. 8.25 divided by 1800 equals 4.6 milliamps. 4.6 milliamps. Now, notice that these two guys are 90 degrees out of phase, so total current ought to be this guy squared plus that guy squared square root, right? So if I go 4.4 squared plus 4.6 squared equals square root, I get a 6.4. Did I have a total current of 6.4? Don't remember. 6.2. Good enough. I'm not keeping that many significant digits to be that close anyway. So, calculate the component current and voltage values for the circuit shown. Boom, I'm done.
That's all you gotta do.
That's all there is. There's only a half dozen polar to rectangular conversions, followed by rectangular polar conversions coming back. Yeah. So if I want to add, I want to be in rectangular form.
What was that again?
If I want to add or subtract, I want to be in rectangular form, which is in the form x plus yi. So where x is in that direction, the imaginary axis is going up and down. If I want to multiply or divide, then I want to be in polar form. R angle theta. R is probably a part of we use R meaning resultant, but we'll go with M for magnitude. Magnitude angle theta. Polar form. Because when I multiply or divide, if I have M1 angle theta 1 times M2 angle theta 2, then that is just M1 times M2 angle theta 1 plus theta 2. And if I have M1 angle theta 1 divided by M2 angle theta 2, then all I have is M1 divided by M2 angle theta 1 minus theta 2. Okay, so that's how I'm multiplying. And if I'm adding or subtracting, and I've got x plus y, then I add the x's together and I add the y's together, and that's how I get it when I'm doing that. And I can throw an I out there. Okay. So one more problem, 43, and then
You go home?
we might, depending on how much time we have after I do number 43. We'll do 43 and then we'll take attendance. So in case anybody left early, get it at the end there. So it's easier to take it. No, just kidding. 43. Determine the Q of the inductor shown below. Determine the winding resistance of the coil. Okay, so Q of the coil is XL over RW. Okay, that's what it's saying. You have to do, that's the hint. Solve for the resistance of the winding resistance of the coil. Okay, so that's our problem. Okay, so we've got 5 volts, 300 hertz, and we've got 4 milliamps, and this guy's in series, so it should be duck soup, right? 1, 2, 3. Except up here in the dark, it's kind of hard to see. 470 millihenry. 750 ohms. Okay. Now, X of L is 2 pi F L. We'll start with there. All right, so 2 times pi times 0.3 times 470 equals 886. Okay, we'll call it 886 ohms. 886 ohms. Now, impedance total. Impedance total is going to be 886 ohms, angle 90, plus 750, plus the winding resistance that we're going to have to come up with. Okay. And impedance total is voltage source divided by current total. All right, well, we know the source voltage, 5 volts. So this is 5 volts, 4 milliamps. Those things are things that are given to us. All right, so 5, that's the wrong 5. 5 divided by 0.004. Okay, 1,250 ohms.
What?
1,250 ohms. 1,250 ohms. Okay, so assuming I can see enough of this at the same time, 1,250 has to equal the square root of 886 squared plus 750 plus RW, the quantity, squared. Okay. Now, we can put that on our graphing calculator to tell us what it is, right? We could do that. I'm going to square both sides. So I'm going to have 1,562,500 is equal to 886 squared, 784996, 784996 plus 750 plus RW quantity squared. Okay, I'm going to take this guy and subtract him from that guy. And I'm going to get 777504. 777504 equals 750 squared, 562,500, 562,500 plus 1500 RW plus RW squared. Okay, so I've got RW squared plus 1500 RW minus something equals 0. $777,544 minus 215,400. Well, now I have a quadratic formula, so I can try to factor it, or I can. What? Or is the video still on? Or I can use the quadratic formula that says if I have an equation ax squared plus bx plus c, then x has to be minus b plus or minus the square root of b squared minus 4ac divided by 2a. Or I could go and use the half quadratic formula, which is a guy that says if I have ax squared plus 2bx plus c is equal to 0, then x would be minus b plus or minus the square root of b squared minus ac divided by a. So I'm going to choose to use the half quadratic formula because it is going to be simpler and have less calculations. So that being the case, RW is going to equal minus b, so that'd be minus 750 plus or minus the square root of 750 squared minus a, which is a 1, times c, which is a minus 215,400 minus 215,400 divided by a, which is a 1. So RW is equal to minus 750 plus or minus. All right, so I've got that number in my calculator. I make it positive, plus 750 squared equals square root, and I got 882, plus or minus 882. Can resistance be negative? Could the wire, yes, I could have negative resistance. Can wire have a negative resistance? No, wire cannot have a negative resistance. So the resistance of the wiring has to be the positive guy. So that's going to be 132 ohms. Q is X sub L over RW. Anybody remember what X sub L was? There it is, 886 ohms. 886 ohms divided by 132 ohms equals 886 divided by 1. You got 150? How about 6.7? Yeah, how about 6.7? 6.7. That is my final answer.
Holy moly.
Okay? See how that works?
Yeah.
Yeah. Now do that quickly 3 more times.
Yeah, do it again.
Do it again. Play it again. Play it again, Sam. That didn't take very much, right? Okay, so I had to find the total. I had to find the reactance. I had to find the total resistance. I had to remember that the winding does have some resistance in it. If I don't remember that, then I can't solve the problem. I can find the total impedance by just the voltage divided by the current, which I know. I know that that magnitude has to equal the square root of the reactance plus the square of the real guy, square root. I then solve for RW, and I come up that RW is, now, can I put that in multisim and show it? That would be a key thing, right?
And we're off.
Okay, so let's look at this now. Yeah. So I need one lousy resistor and one lousy inductor. And all I'm doing is what do you mean wrong? What are you wronging about? Can't be wrong yet. Haven't done anything yet. I know it is. All right, now I need a amp meter, and a horizontal amp meter would be good, and it needs to be DC. No, AC. It needs to be AC. Okay, this guy is 470. 470. And this guy needs to be 750. 750, are you sure? 750.
Because you're writing on the wall there.
All right, and then we're going to go and rotate these guys. All right. Now, when I get done, I better not have 4 milliamps, right? Because I haven't put in the winding resistance yet. I don't want to do that. Okay, turn it on. Okay, so I turn it on, and I see, oh, well, of course I got that, because I didn't bother to change this guy. All right, so I want 5 volts. 5 volts and 300 hertz. All right, that's better. Okay, so I have too much current. I got to get rid of some. The only way I can do that is do it by adding winding resistance. So where is the tolerance, the footprint, the initial conditions? Darn, I can't put any winding resistance in, can I? There we go. Leakage. 130. 133. 132. 132.
Yes.
Hey, turn it on. Okay. All right, be that way. Stupid thing, anyway. All right. Well, we're gonna do something different. Where's the resistors? There's the resistors. All right. So this is my winding resistance now. There. There. We wanted this to be 332 though, didn't we? 332. And then we want this guy here to be unfaulted, none. You stupid thing anyway. Alright. And now we should see 4 milliamps. Close enough. Is that close enough? Now that we see, and we'll put him there, we'll put over there. We'll go and do this. You see that he's 4 milliamps? Now, what does the quality mean? We said the quality was 6.7, right? How are we going to measure that? Well, we have a Bode plotter right here. And we're gonna hook up the input to the Bode plotter. And we're going to hook up the output. And the output's going to go around my inductor. And we're going to turn them on. And we see something happening. Oh, let's see, we don't want that, we don't want that. We want phase or do we want angle? Okay, so there's the angle. A little bit of an angle thingy. Let's see if we go up to 10. Okay, we dropped it down. So what we're looking at, we'd like to see a little bit different curve there. How come our curve isn't what we want to see, I wonder? I mean,
Do you have to look it up after the resistor, or you want to do?
no, I don't know. Can't do that. Yeah, it has to be after it has to see this resistor here is the winding resistance. It's in that guy. They're in the same thing. Well, we don't have to go that far out. Let's go to mega. So where is this guy? Here's 1 kilohertz. So we'll go kilohertz, and we'll drop this guy to hertz. Minus 15 dB to minus something else dB. That ain't working. I was expecting to see something a little bit different on my Bode plotter. Yeah, yeah, I know. What I was expecting to see is I was expecting to see something like that, and I'm not going up and down, and so that is I'm only going up. Now at higher frequencies, something's wrong. Something's wrong. I don't know what it is. At higher frequencies, this guy becomes an open. And at lower frequency, he becomes a short. So why am I doing what I'm doing, I wonder? Oh, let's change that. Minus 50. Minus 10. Okay. Minus, that might be all right, minus 10. Go back to minus 10. And then we'll come out here. We'll go back out to megahertz. So I'm why am I not coming back down? I'm asking myself. Yeah, I think so, 20. So I'm doing that. I'm in magnitude. I'm in log. There's my phase. I see. No, don't want that. This is what I want. But how come, if this becomes an open, then of course I'm going to get the whole thing coming across. So that would be correct. But how am I going to show that this is a Q of 6 point something if I don't have a bandwidth or I don't have something else? Well, I guess that means that I failed to show my answer is correct in multisim, except that I can get a if I had a 132 ohm winding resistance in the inductor, I do get 4 milliamps. So that sort of implies that I have the right answer, but I can't show that my Q is correct.
So because you didn't clear the faults on the inductor?
I'm sure I did, yeah. You're not sure I did? I'm sure I did. Yeah, none, no faults. Okay, well, I guess that's good enough.
Yes,
Is that good
I
enough?
agree.
Yeah. When's the next test anyway?
I hope never.
Oh, yeah, the day before Thanksgiving. Cool.
I don't know what to be so thankful about.
Huh?
I'm
You don't
barbecue
want
for
it.
that shit.
You don't want the test after Thanksgiving. Yeah. Maybe we should have a take-home test and make it twice as hard. What do you think?
Yeah.